we will discuss strength of gravitational field. First of all, I tell you strength of gravitational field on the surface of the earth, you know, is denoted by G, and it is on the surface of the earth is equal to 9.81 Newton per kg, or the same as 9.81 meters per second square. It is based to help give the units of Newton per kg. First is that thing, you know it very well in your from O levels also. And then another thing which I tell you, I'll always be taking in this chapter, I'll always be taking capital M as the mass of the body due to which the gravitational field exists. This will be the mass of the body due to which gravitational field exists. This is mass of the body due to which gravitational field exists, and I will always take M small as the test body, which is for the testing purpose. So suppose if this is the gravitational field, this is the point of infinity, where point of infinity is the point actually where no gravitational field exists, or it's very far, we can't define it. This suppose mass, suppose this is Earth, this is Earth's mass is M. Suppose I want to find the gravitational field strength over at this point G. I define first the definition. What is the definition? Definition must be perfect. I will give two definitions here, both are okay. First one is, I say force per unit mass. Force per unit mass means whatever the force is exerted, if I place here 1 kg body, whatever the force is being exerted here, that is the strength of gravitational field. The other definition is I can place, suppose here mass M, and the force exerted by this is F. So this force F is on mass M. So on 1 kg, this becomes the force per unit mass. So on 1 kg, the force must be F upon M, and that is the strength of gravitational field G. We define G is equal to F upon M and then explain. G is strength of gravitational field. F is force, M is mass. Mass of the body placed in gravitational field, it's the force of attraction, you can further say. So this is the definition, proper definition. Now sometimes it is confusing. Some students think that G is inversely proportional to test mass. The strength of gravitational field depends upon the test mass also. No, it doesn't, because actually it is the constant. You will see it's the per unit mass. Whatever the value of this M, when this divides, it becomes the value for 1 kg. So it's actually per kg. So this mass is constant here. So no effect of this one, but it is rather the effect of the force. Now actual formula which shows clearly, sometimes comes for to proving also. They say prove this. They say G is equal to Gm upon R square, where terms of the usual meaning. Usual meaning, when G is the strength of gravitational field, capital G is the universal gravitational constant, M is the mass of the body due to which the gravitational field exists, and R is the distance of the point from center of the body of mass M. Suppose in this case, if this M is the body due to which the gravitational field exists in its center, and this is its gravitational field. Now if I want to find the gravitational field at this point, which is at distance R from here, I will just place a mass M here. When I place, I'm just giving a proof of this one. Since I know that G is equal to F upon M, I can write this as G is equal to F into 1 upon M. But by universal gravitational law of the Newton, I can say what the force of attraction here on this body by Newton's law. This capital M, this small m, I will say it is G M upon R square into 1 upon M. So this R is the distance from this body up to this one. So M is cancelled M, so G is equal to Gm upon R square. It is clear, the strength of gravitational field does not depend upon the mass of this one. It depends upon the mass of this body and the distance from which it is placed. So G is equal to G upon R square. Let us see for a body, how can this G varies inside the earth suppose if this is Earth, inside the Earth and outside the Earth, how should it vary? I'm just going to the graph I'll be going, but before going to this one, I will again teach this thing, how this is to be proved. We have to prove G is equal to G upon R square. I will define the strength of gravitational field first. Strength of gravitational field is defined as force per unit mass, so G is equal to F upon M. I can write this G is equal to F into 1 upon M, but this F is the force of attraction between these two bodies, and it is given by the formula G and M upon R square. So this M and M cancel out each other, so this becomes G is equal to G M upon R square. Now sometimes it says how the graph is, how the graph is varying. For example, if this is, I'm going for the Earth, if this is Earth, if this is center, this is the radius of Earth, this distance is the radius of Earth from center, and this is twice the radius of Earth, and this is what, suppose thrice the radius of Earth. So how the G varies here inside, and here G, what is the value of G, what is the value of G here, what is the value of G here. Actually the value of G here is exactly G, here is G upon 4, and here is G upon 9. Simple, why G upon 9 is here value? Because you see the G varies as 1 upon R square. So when G varies as 1 upon R square, if this is 2RE, so G varies as 1 upon 2RE square constant, so this 2 becomes 1 upon 4, so G becomes 1 upon 4. If you place in this value also, G is equal to GM upon R square, so at the surface of G is equal to GM upon RE square. But at 2RE, this becomes G is equal to GM upon 2RE whole square, this becomes G is equal to GM upon 4RE square. So this is value of G at the surface, so this becomes G upon 4. So in that way, this will be G upon 9 and so on. How is the graph determined? Suppose here I am taking this one, distance from center of Earth. Distance from center of Earth. And this is the value of G. This is 0. This is the radius of Earth. Suppose this one is the radius of Earth. This is twice the radius of Earth, this is thrice the radius of Earth, and it's 4 times the radius of Earth, suppose. Now at the radius of the Earth, the value of G is fixed, which is G, or 9.81. I'm taking G. Inside is always a straight line graph. This inside the surface of Earth. Inside the surface of Earth. Or it can be for any planet. This means inside G is directly proportional to distance from the center. G is directly proportional to distance from center, and inside we will be using just the ratio method. We can have this formula at the surface of the Earth calculated from other given formula, given value, and we can set a ratio. Then afterwards, if the value of 2RE, value becomes 1/4 G upon R. This is G upon 4. At 3RE, value becomes G upon 9. And 4RE, value becomes G upon 16, and so on and so forth. So I have this graph. This will never be, because acceleration to gravity cannot be 0. It will be 0 at very infinite point. Actually, this is at the surface. This is outside the surface. Now clearly this tells us if something is inside the surface, then ratio method will be used. Ratio method for finding any value of G inside the surface. And if it's outside the surface or at the surface, then value of G can be found by the formula G is equal to G upon R square, where R is greater than or equal to RE. Only this formula is valid for this case. When R is less than RE, you have to use a ratio method. Then another thing also, why this R is always the distance from center. It's not the distance from surface. This is the graph inside the surface of the straight line, directly proportional. This is the moon, and this is the curve, and then the value of fixed. Sometimes examiners say in terms of exact values. So distance from center of Earth, 10 power 6 meter, because you know radius of Earth is 6.4 10 power 6 meter. So I'm going for the exact terms, and value of G is Newton per kg is 9.8. So this will be 9.8. This will be 9.8 upon 4. This will be 9.8 upon 9. this will be 9.8 upon 16, and this value will be 6.4 into 10 power 6 meters there, and this will be 12.8, and this will be 19.2, and this will be 25.6, and so on. So suppose I can say what is the value of G here. It's a 12.8 10 power 6 meter. The value of G is 9.8 10 power 4 meter, and this is actually this 3 RE value. So this is in exact terms, and this one in terms of G. Sometimes examiners say the graphs not from center, but it is a distance from surface of Earth. When surface of Earth is there, so this graph is now finished, but the values will remain same. Values will remain same. Now you can see, now this is the value of G in this graph, this one. This is exactly value of G. If in exact terms 9 Newton per kg, this will be 9.8. This actually this one now, this one, which is 0, not 6.4, the center. Now this value from here will be RE, not 2 RE. RE are 6.4 in 10 power 6 meters, and this will be now 12.8 in 10 power, and this will be now 19.2, and so on. So this will be 9.8, and this will be this one, 9.8 divided by 4, 9.8 divided by 9, this will be 9.8 divided by 16. In exact terms, these are the exact values or terms, but suppose sometimes not exact terms, how the values will change. For suppose I can take a graph of acceleration due to gravity or strength of gravitational field against distance from center, distance from surface of Earth I am taking. You can take any planet, but then not RE. So this is 0, this is RE. 0 means at the surface of the Earth, value of G will be definitely G. RE means it is at a distance twice the radius of the from the center. So this will be G upon 4. And 2RE, this is actually thrice the radius of Earth. This will be G upon 9. And 3RE, this will be actually G upon 16, and so on. So this will be the line. This is the line when distance from surface of Earth. This from surface of Earth. See the 4 graphs, the difference in these 4 graphs. So this is the acceleration due to gravity. So again I will say, we define acceleration due to gravity by the formula G is equal to F upon m as the force per unit mass. Then we can prove it as G is equal to F into 1 upon m, and F is Gmm upon r square into 1 upon m. M cancel out, so it's Gm upon r square. Then we can have the graphs. 4 graphs in which distance from surface of Earth or distance from center of Earth is different. Then we have the inside is G is directly proportional to distance from the center, and outside G varies as r square, and we use the formula G is equal to Gm upon r square, and r is greater than or equal to radius of Earth.